Welcome back. This is our final installment in long sequence on mirror descent. And to wrap this up, I'm actually going to go back to the beginning and tell you about a different view of the mirror descent algorithm. And actually, this is closer to how it was originally developed. So, big picture here is, this is what we're trying to optimize again. So a big picture here is that we want to think about phi. This is called a mirror map. And this is because we want to think about the gradient of phi as mapping to a dual space. So let me draw the picture. Basically, want to think about primal space, as it's called, is the space where x lives. All the points that we have, x star, our trajectory lives in the x space. So x star is somewhere in here. Actually, this is the set D, which is the domain of phi, and somewhere inside of here is our set X. That's what we're optimizing on. So X star, our optimal solution, is somewhere inside the set X, and at some point we've been moving around, and we finally have reached the point xt. Over here is our dual space. You can think of the dual space as being the space of things that you use to take dot products with things in the primal. Remember that in the last lectures, especially the one where we talked about the proof of mirror descent, I mentioned that you're never going to see in the proof of mirror descent a gradient being added to a point. This is not like, usually we're used to thinking of gradient descent or subgradient descent as saying that you move from xt to xt minus a multiple of the gradient or the subgradient. But if you look back at the proof, you'll see that that really didn't appear anywhere in the definition of the algorithm or in the definition of the proof. So the gradient of phi is our back and forth between the primal and the dual. And remember that one of the requirements for phi to be a mirror map, which we talked about 2 lectures ago when we were talking about the proof of mirror descent, is that phi has to be strongly convex with respect to the right norm, of course. And the gradient of phi, this is where this came from, has to be surjective. So in other words, the gradient of phi evaluated on D gets us everything. So any point I choose in the dual, I know had to come from some point in the primal. So let's look at what the algorithm does. It starts from a point xt, and it uses the mirror map to map this to a point in the dual. And this point will be, I'll call this the gradient of phi at xt. From this point, it moves to the gradient of phi of xt minus eta times subgradient of f. So what's happening here is, again, note that I'm never adding the subgradient g to the point x. I'm only doing that kind of operation in the dual space. So in the dual space, I take gradient of phi at xt. That's the dual mapping. That's a mapping of my point xt, and there I do a gradient step. Now, because of the surjective property, I know that there is some point in the primal which maps to gradient of phi of xt. So in other words, this has to be some image of, it has to be the image of some point that came from the primal. So I will just call that, I'll name that point, yt plus 1. So yt plus 1 is somewhere here. It may be in x, it may not be in x, but I know that its image under the gradient of phi is equal to this gradient phi of xt minus eta gt. So let me draw y. So this is my yt plus 1, which I basically get, maybe I should stick with my color consistency here, which basically comes from this image, the pre-image of the gradient step in the dual. Well, and now I finally just need to get myself back into my constraint set X, and this happens by projection. So I project, and this is my point xt plus 1. So the final movement in the primal, this is what the mirror descent algorithm accomplishes. It moves me from xt to xt plus 1. And what is this projection here? Oops, let's see where I can write it down here. This is the Bregman projection. So it is xt plus 1 is equal to the argmin of d phi of x yt plus 1 subject to x being in my set x. So this is a different view of mirror descent, and it's closer to the origins. And we saw some similarities of some elements of this when we were talking about the specific example of x being the simplex and using the negative entropy as our mirror map phi. So the connection to our example, where phi of x was equal to sum of xi log xi, and x was equal to the simplex, which is non-negative x that's summed to 1, then using mirror descent to minimize a function f of x subject to x in x, what we found is that starting our mirror descent update looks as follows. We start from xt, then yt plus 1 is the point such that the gradient of phi at yt plus 1 is equal to the gradient of phi at xt minus eta times gt. gt is an element of the subdifferential of f at xt. So this defines yt plus 1. For our specific example, we saw that yt plus 1 was equal to this scaled xt. So the ith element of yt plus 1 was equal to the ith element of xt scaled by e to the minus eta times the gradient of f evaluated at xt, the ith element of that. And finally, the projection is easy to compute in this case. Xt plus 1 is the argmin of d phi of x yt plus 1 subject to x in the simplex, and working out the details in this example, you'll find that xt plus 1 is just equal to yt plus 1 divided by the L1 norm of yt plus 1. So that's another view of mirror descent. We'll pick this up next time with a different topic.